All right, today we're going to talk about equivalence relations and antisymmetric relations. So a reflexive property is A equals A. Our symmetric property is A equals B and B equals A. And our transitive property, if A equals B and B equals C, then A equals C. And there are special cases such that if there are less than two objects in a relationship and the relationship is reflexive and symmetric, then the relationship is also transitive, even though we're not completing this statement. Also, there is no restriction on further relationships past completing this. So if you have an additional reflexive point D, that's okay. This still holds. And then if we have all three of these, we have an equivalence relation. Antisymmetric relation is then if we have a point AB that is part of the relation, then BA cannot be part of the relation unless A equals B. That's the only way that we can have antisymmetric. So let's see what some of these look like. For these, we're going to be using the set A for the first, I think, 5. And we're going to have our rules up here. So let's take a look at our first one. We have 1, 2, 3, and 4. 1, 1, 2, 2, 3, 3, and 4, 4. So when I circle it, that just means that it's coming back on itself. And this one is reflexive because it is including itself. It is symmetric because symmetric also holds that principle of A equaling A, or A equals B, I guess. And then antisymmetric also, if it equals itself, or if A equals B, then it holds as well. So it is all three of those. Let's move on to our second relation. So we have 1, 2, and 3. 1 is on top of itself. And then we're going to go from 2 to 3 and 3 to 2. For this one, all this is symmetric, right? So this is a reflexive right here, but all of them have to be reflexive for it to count. And then it is not a antisymmetric because we have a symmetric principle right here. And then transitive was never completed. For our third one, we have 1, 2, 3, and 4. 1 is on top of itself. 2 is on top of itself. We have 2, 3, 3, 2, 3, 3, and 4, 4. So for this one, we have reflexive, right? All of them are on top of themselves, and it's symmetric. And that will be all we can do with this one. So for our last one, let's take a look at, or no, I guess we're on number 4, sorry. So again, 1, 2, 3, and 4. So 1 is on top of itself. Then we have 1 to 2. We have 2 to 3. 2 to 4. 4 to 2. And 3 to 4. So for this one, we only have transitive. So we go from 2 to 3, 3 to 4, and 2 to 4 to complete our statement. So for our last one, we have our 5. If we have 1, 2, 3, and 4, let's make these a little better. So 1 is on top of itself, then we go 1 to 2. We also have 1 to 3, and we have 2 to 1, 2 on top of itself. We have 2 to 3, and we have 3 to 1, 3 to 2, 3 on top of itself, and 4 on top of itself. So this one, we have reflexive, everything is on top of itself. We have symmetry, we have transitive as well. So we have from 1 to 2, 2 to 3, and then from 1 to 3, and then, I mean, we can also do that with other points, but it only has to be proven once. So we have all of those, and then this, by definition, then is our equivalence relation, or an example of it, because we have all 3 in 1. Next, we're going to use set B. So we have 1 and 2. 1 is on top of itself, and 2 is on top of itself. So this is reflexive, and then it's on top of itself. It's symmetrical by the same principle. It is transitive because it is less than 3 points, and it is reflexive and symmetrical. Remember that we have that special case. So this is an equivalence relation. And then it's also a antisymmetric because A equals A and B equals B. So yeah, it is all of them at once. And with that, we're good with this lesson.